Hello dear friends, this is Bhushan Dravekar going to discuss about ion exchange chromatography. Disclaimer: this presentation is made for educational purpose only. The information provided here is taken from both online and offline resources published in a standard textbooks. After the successful completion of this session, students are able to explain the concept of ion exchange in chromatography. They are also able to distinguish between anion and cation exchange chromatography. They can also apply the knowledge of ions to improve the efficiency and reproducibility in process of separation, create a research project based on ion separation principle. Ion exchange phenomenon is based on adsorption, where electrostatic force is a predominant force used. Electrostatic force holds the ion to charged functional group on the surface of ion exchange resin. The adsorbed ion replaces that are on the resin surface on an 1:1 charge basis. Let us take an example here. In this present example, sodium ion is going to replace this hydrogen ions. So overall, ion exchange chromatography mainly based on an adsorption phenomena, where resin is used as a stationary phase along with a suitable mobile phase. History: the first ion exchanger were synthetic resins designed for a different application such as demineralization, water treatment, and recovery of iron from waste. The first ion exchanger designed for the use with biological substance, where cellulose ion are cellulose ion exchangers are developed by Peterson and Sober. Ion exchangers based on dextrine are commercially called as Cephadex, followed by those based on agarose polymer, Cepharose Cl6b, and cross-linked cellulose DEAE Cephacell, where the first ion exchanger matrices to combine the spherical form with high porosity, leading to improved flow properties and high capacities for macromolecules. Mechanism for ion exchange chromatography: it is thought to be composed of 5 distinct steps. Diffusion of ion through the matrix surface. It is here quick homogeneous solution is formed. Diffusion of ion through the matrix structure of exchanger to the exchanger site. It depends on the degree of cross linkages of exchanger and concentration of solution. So here it provides a control the rate of whole ion exchange process. Exchange of ion at the exchanger's site: the more highly charged the molecule to be exchanged, the tighter it bind to exchanger and less readily it displaced by other ions. Diffusion of exchanged ion through the exchanger to the surface and followed by selective desorption by the eluent and diffusion of the molecule to the external eluent. The selective desorption of a bound ion is achieved by changes in pH or their ionic concentration, or altering their affinity by elution. The affinity elution the ion having greater affinity for exchanger than for bound molecule is introduced to the system. So these are the ion exchange resin, which is an heart of this ion exchange chromatography. Usually polymeric resins are made in 3D network by cross-linking hydrocarbon chains. The resulting resin is insoluble and inert and relatively rigid. The ionic functional group are attached to this functional group. Here a representative diagram and the actual resin beads has been shown in this figure. Characteristics of ion exchange resin: uh, it should be insoluble in aqueous medium, it should be denser than water so that it can remain in this water, do not float on the solvent system. It should have less porous, porous polymeric structure so that it can get swelled easily. It should be inert in nature and should have large exchangeable sites. It should have high degree of cross-linking properties. Classification of ion exchange chromatography is pretty simple, that based on the types of ion exchange resin used. So here cation exchange resin and anion exchange resin. Cation exchange resin are pretty acidic in nature. Therefore, they are further subdivided into strong acidic cation exchange resin. Example is sulfate. Second one is weak acidic cation exchange resin. Example is a carboxylic acids or their derivatives. Second one, anion exchange resin, strong basic anion exchange resin. Example is alcohol. And weak basic anion exchange resin. Example is amine. So in short, strong acid or basic cation anion exchange resins are the examples, or these compounds are mainly from the stronger acid or basic side, whereas weaker acidic basic cation anion exchange resin are primarily taken from your organic acids or bases. Factors affecting separation of ion. So the very first factor is the charge, intensity of a charge. Example, thorium. It carries a 4 plus charge. So naturally it will uh, bind much faster as compared to aluminium, calcium, followed by a sodium, right? Second important factor is size. As you keep decreasing the size, you will your ion got more hydrated because it got surrounded by more solvent molecule, what we can call it as an hydration of a molecule. And since these excess of solvent molecule decreases the affinity of that particular ion towards the counter ion. Therefore, if the size of ion is much lesser, your affinity towards counter ion is decreases, and vice versa. Example, lithium is fastly absorbed as compared to proton, sodium, ammonium, potassium, like this. Third important factor is the concentration. Higher the concentration of some ion in solution, higher is the affinity of ion with that particular resin. Use of complexing agent and ability to form complexes. It is affinity with resin decreases with increasing complex formation affinity. So here the ability to form a complex, its affinity with resin decreases with increasing complex formation affinity, means that compound should able to form a complex. If your complex formation ability is being increased, then naturally that affinity of this complex towards this resin is decreases. Fifth one, nature of resin. Resin having a typical, it depends on the type of resin. Resin having a spherical shape, having high degree of cross-linking and cross-linking property, which allows to link a big, since it forms a maximum surface area. It provides a maximum surface area which increases the strength of a functional group, which decides the ability for exchange of ions. As the cross linking in this polymer resins are increasing, means it also increases the ability of this counter ion to get entangled with this cross linked mesh. Effect of pH, the pH can affect the separation in several ways. The ionization of resin in solution depends on the pH, especially if the functional group is weakly acidic or basic. The strength of acid and bases or the hydrolysis of salt, ionization of functional group of the resin, all are strongly depend on the pH of the solution. For better ion exchange, weak acidic anion exchanger has to use in alkaline medium. Similarly, weak basic anion exchange has to use in acidic medium. Now, ion exchange capacity. Efficiency of any ion exchange process depends on the exchange capacity of resin. The number of milli-equivalent ion exchanged by 1 gram of dry resin is called as ion exchange capacity. When 1 gram of cation exchange resin is soaked in HCl, to convert the resin in H plus form, it is then placed in water. The glass tube like that of burette is packed with the resin. 10 ml of 0.5 normal solution of sodium sulfate is placed on resin column. The elution is carried out using distilled water. The eluate is collected in conical flask and then titrated with 0.1 normal NaOH solution using phenolphthalein indicator. Volume of NaOH required for the titration is found out and cation exchange capacity is determined by using formula V into N upon W, where V is volume of burette reading, N normality of NaOH, and W weight of dry resin. Experimental technique, mainly it carries 5 steps: loading of sample, adsorption of ion selectively, elution, start of elution, where the adsorbed ion started eluting, end of elution, and lastly the column regeneration. Instrumentation, again it is pretty similar with your HPLC, which carries pump, injector, columns. Here specially resin are used in this column material, oven, detector and readout system. Application: preparation of demineralized water, separation of lanthanides, separation of amino acids, determination of concentration of trace constituent, separation of similar ion, interfering cation anion. Thank you.